Welcome to the Advanced Fluorescence Microscopy and Image Processing course. So today is our lecture 17th and that is the third day of our workshop on ImageJ or Fiji based image processing. And today I will show you how to write macros in ImageJ, how to do intensity measurement and how to do colocalization analysis. So let us begin with the ImageJ macros. So what is ImageJ macros? Okay. So let's say, suppose for the same experiment, you collected n number of movies or n number of Z-stack images. Okay, let's say there are 50 such images of the movies. Let's say HeLa cell 1, HeLa cell 2, HeLa cell 3, HeLa cell 4. So in series, you will capture 50 images of the movies using your microscope. Okay. Now, all these movies or the images you want to process in the same way. Okay, let's say first step is you want to split the channel, then you want to give colors, then you want to crop them in particular dimension, then you want to make montage, and then you want to put the scale bar in all these 50 images or the movies. Okay, so if you do that manually for all 50 images, it will take you a lot of time. Okay, so ImageJ or Fiji provides such kind of macro writing or the macro recording. So how it works, let's say you just process your first image, and while you are processing your first image, the ImageJ macro recorder will record the steps that you are following. So that recorder will record that, okay, first you split the channel, then the second step you give color to different channels, then in the third step you crop the images, in the fourth step you make the montage, and in the fifth step you put the scale bar. Okay, so that macro recorder will record all these steps while you are processing your first image, and then you just give a command so that it will do the same processing for the rest of the images or the movies. Okay, so first step it will record, while you are processing the first image it will record the steps, and the same steps it will apply to rest of the images or the movies. So it will automatize the image processing pipeline. It will save significant amount of your time. So today I will write you, I will show you how to record the ImageJ macros. And believe me, for writing ImageJ macros, you do not need any prior knowledge of the programming languages. Okay, because it automatically record the commands based on steps that you follow on your image. Okay. So let us see how it works. So first of all, where this option exists in this ImageJ software. So it exists if you go to the plugins menu and then macros, and there is an option of record. Okay. So let us do that. So this is plugin, then macros, and this is the record option. Okay. So if I click this, then it will start recording the steps that I am following with image number 1. Okay. So I will show you. First I need to open the image number 1 to follow these steps. Okay. Okay. So how we'll do? So see, first we'll open an image, then we'll start the macro recorder so that it can record the steps that we are following, and then perform the actions that you want. And when you are done, click create and save the macro. So that way you can save the command line that which command needs to be followed on one particular image. So let us do that. Okay, so what I will do, I will minimize this, and in this folder I will show you that there are 3 movies. So in this folder you can see there are 3 movies: 4D image 01.dv, 4D image 02.dv, 4D image 03.dv. So 3 movies are there. So what I will do, I will record the macro using image 01, and we will ask the macro to apply the same steps on image number 2 and 3. Okay, so let us open this image number 1 first, 4D image 01. I'll just go to File, Open, and then I can see this folder, and I'll open this 4D image 01.dv. Okay. It will ask me that which kind of movie it is. So I will mention that the stack order should be X, Y, channel, Z, and time. Okay, it's a hyperstack. So it is opening the file. Okay, so see, now first let us understand this file. So here you can see C is 1 by 4. So there are 4 channels in this file. Okay, so red, green, blue and magenta. There are 4 colors, 4 channels in this file. Then Z 1 by 45. So there are 45 Z steps and we are at the first step. So here you can see there are 2 scroll bars. The first scroll bar is for the channel and the second scroll bar is for the Z position. Okay, so if I go to the middle of this movie, okay, middle of the Z stack, okay, then you can see some structures. And when you open a file, you need to adjust the brightness and contrast to make your structures visible. Okay, so I won't do anything now. I am just explaining the video because before I perform any steps, I will start that macro recorder so that it will record the steps that I am following on this movie. So I just open this movie. Okay, and I am just explaining you that it has 4 channel and it has 45 Z stacks. Okay, and what is our goal? We will process it in such a way we can make a montage which generally people show in publications. Okay, so let me do this. Let me go to plugin, then macros and start recording. So I will start record. So this is the macro recorder has opened. So now whatever the steps I will perform on this image, it will keep recording. Okay, so let's say first what I will do, I will open this brightness and contrast adjustment tool and I want to make sure that all the structures are visible in this image. So I bring it to the center of the Z stack, and now using this intensity measurement, sorry, not intensity measurement, this is brightness and contrast adjustment tool, I'll just push this threshold so that only the bright pixels are visible. Okay, so now you can see. So this is what I want to see. These are single molecules of mRNA. This image is actually from the single molecule fish experiment. So in the first channel, you are seeing the single molecules of mRNA. Then in the second channel, you will see the transcription sites, 2 transcription sites per nucleus. These are 2 transcription sites per nucleus. In the third channel, you can see one protein labeled with GFP. So I am adjusting the brightness and contrast of all the 4 channels. And this is a DAPI channel. I'll just make it little brighter. Okay, so I adjusted the brightness and contrast for all the 4 channels. Now the next step is I have to give the colors. Okay, so let's say for this channel, I will, from this lookup table, this is a LUT, that is lookup table. So I will give it a color of magenta or maybe yellow. Okay, then to next channel, I'll give color green, but I think it is changing. Okay, then the third channel here, I will give a color red, and this channel I'll give a color magenta. Okay, so the single molecules of mRNA are in magenta color, then this transcription sites are in red, the nuclear protein is in green, and the nuclei are in yellow color. Okay, so I gave 4 colors to these 4 channels. Okay, now I want to merge all the Z steps. So let's say there are 45 Z steps for each channel. So I want to merge all the 45 Z steps, or maybe I can see instead of merging all 45, if I merge Z steps from, let's say, number 29 to 17 to 29, that will be enough. 17 to 29 because that contains the nuclei. But let me check. In first channel C, I can still see some molecules. So I will go little further and I will merge from this stack, that is 14 number Z stack, to 31, 14 to 31. So go to image, stack, Z project, and I will ask the software to merge 14 to 31 Z stacks in maximum intensity projection. Okay. So this is the maximum intensity projected image. So now the Z steps are gone and only 4 channels are there, but they are all merged channel, means or merging of all Z stacks. Okay. And now I want to make one representative image for the paper. So what I will do, I want to crop a small area where I can show only few cells, not all. Okay, so I'll crop this small area like this. Let's say the area should be square. So 366 by 366 pixels. Okay, this is 368 by 368 pixel area. Okay, that I selected, and I will also open ROI manager to record the position of this ROI so that I can use this ROI later on. Okay, so I recorded the position of ROI. Okay, and now I will use the crop option, image and crop. Okay, so this small area is cropped of 368 by 368 pixel. Okay, it has all 4 channel information. Okay, and now the next step is I want to make the montage. So I'll make montage. So here I can define that I want these 4 channels as 4 columns, 1 row. First slides, last slides, all these things are okay. Border width to 2, font size to 12, and fine. Okay, let me see the montage. So this is the montage that generally people show in publications. Okay, and it looks good to me. Okay, and let's say I want to put a scale bar here. So I will find out the scale bar option, and here I have the options to select. I want to show 5 micrometer, height is thickness and font size and everything is okay. And the position, instead of lower right, let's say I want to put it on lower left. So it is on this side and on the first image. Okay, so this is fine. And okay, and let's say press OK. Okay, so I put the scale bar as well, and fine. And then I want to save this montage file, save as TIFF in, let's say, processed image Gunjan folder, and I want to give it a name montage1 because it is from file number 1. So I give it name montage1. Okay, so I saved it. I also want to save it as PNG also so that I can use it for some Microsoft PowerPoint or Microsoft suite of applications. Okay, with the same name montage1. So I saved it at PNG also. Now you can see this macro recorder has recorded all the steps that I followed for this image processing. It has recorded all the steps. And now the last step, what I will do, I will close all these things, or close all this image, so that also it will record. Close. Do you want to save the max 4D image 01 TV? Yes, let's say I want to save it. So I will save it in the same folder. So let's say later on I want to change something, brightness, contrast, something, I can do those kind of adjustment. So I saved it. Okay. And then I want to close the original image also. Okay. So I close the original image. So this is my macro. Okay. All the steps that I follow, those are recorded. And I will now press this create button. You can see this create. So this macro is created, and I can save this macro also. Open file, save as, and in the same image, same folder, I'm saving this macro as. Okay. So this macro is ready. Now the next goal is to open the second image, and I want all the steps to be followed automatically. Okay. So what I need to change in this macro. So let's say all these things it performed on the 4D image 01. Now the file name of our second image is this one, 4D image 02. Okay. So let me open this file. Open and 4D image 02. So see, previously we worked with this file 4D image 01. Now we want to follow all the steps on this image 4D image 02. So I'll click on this file, open it. Again, I'll open it as a hyperstack with XYCZT. Okay, and now I want to follow all the steps same on this image. Okay, so what I need to change here, wherever the file name is mentioned, let's say here, let's say select 4D image 01. So this file name I will change to 02, because now this file name is 4D image 02. Then it also saved your previous file as TIFF and PNG as montage 1. So that name I will change to montage 2, because this montage is coming from second number file. So it will save it as TIFF and PNG file with the file name of montage 2. And if there is any other file name mentioned, so you just have to replace 01 with 02 to apply all these functions on the second image. Now see, you open this image, and similarly you need to adjust the brightness and contrast. Brightness and contrast will not be adjusted automatically through this macro. Okay, so what I will do, again I will go to this brightness and contrast adjustment tool, and I'm at the middle of the Z stack, and by keeping middle of the Z stack I will adjust the brightness and contrast so that I can see the structures. So let's say in the first image the single molecules have mRNA are visible now with this brightness and contrast. Okay, then for second channel I need to adjust it a bit. Okay, these are the transcription site. And in the third channel there is a GFP labeled nuclear protein. So let me adjust the brightness and contrast for that. And in the fourth channel is the DAPI. So here also I will adjust the brightness and contrast like this. This thing you need to do manually. This macro will not do it automatically. And also the colors also you have to give manually. So you will select this channel, then you will give yellow color to DAPI, then green color to this GFP channel, red color to this transcription site, and magenta color to this single molecules of mRNA. Okay, so you give all these 4 colors, and that's why we already gave the colors and all. So I'm just removing this initial steps from the macro, because we already did it, no need to run it by the macro. Okay, so macro will start from this step. It will make the Z project of this file, then it will make a rectangle of this dimension, it will add it to ROI manager, then it will make montage, it will put the scale bar, it will save both the montages at TIFF and PNG, and then it will close all the files. Okay, so now I will just press this run button so that all the steps will be followed on this file, and the montages will be saved in the same folder with montage2, okay, with the file name of montage2. So let me press this run button. Image 5D required in line 7 run, make montage. Okay, so there was an error here, so I will ask it to run from here. Okay, so it actually stopped at this point because this is a different type of montage it was asking for, but we use a different montage command from here. So I will select this step and I will ask to run selected code. Okay, instead of run the entire code, I will go for run selected code. So this montage was made, and the montages are saved in your folder. So let me show you here. In this folder, you can see montage2. Okay, so this is your montage2 with 4 colors. Okay, but you cannot see the scale bar. Let me see why the scale bar is not here. Ideally, it should have kept the scale bar also, but the scale bar function in the TIFF file. I can see the scale bar like this. Here the scale bar is there. In PNG file I can see, but in TIFF I am not seeing the scale bar. Here the scale bar is there in PNG file. Let me see whether in the previous TIFF file the scale bar was saved. This is a PNG file, the scale bar is there. And in montage1 also, in the TIFF file the scale bar is not saved. Okay, so it is not saving the scale bar in the TIFF file. Now let us try this macro on the third image, that is 4D image 02. Okay, so I'll open it. File, open 4D image 03. I will open it as a hyperstep XYCZT. So this image is open, and what I need to change here is I need to change the file name 4D image 03, and montage, the output file will be montage3. Okay, and I have to manually adjust the brightness and contrast for each channel. So I'll go to the middle of the Z section, okay, and I will adjust the brightness and contrast for each channel. Okay, and now I'll give colors also. This is yellow color, then the next channel here green color, next channel red color, in the first channel magenta. Okay, so I gave 4 colors to 4 channels, and now to process all these steps I want to make Z project, then rectangle ROI, then I want to make montage, I want to crop it, make montage, put the scale bar, save it as TIFF and PNG, and then close all the files. Okay, so I just need to press this button so that all the things is processed, images are closed, and the montages are saved in that folder. So let us go to that folder, and here you can see montage3. This is your montage3, and this is a TIFF file, so you cannot see the scale bar, but if you open the PNG file, you can see the scale bar. one of the reasons that why the scale bar is not visible in the TIFF file, because we forgot to tick mark the option of embed scale bar in the TIFF file. Okay, so you can see, so this way now you can have an idea that what are the steps you want to follow on one image. The same steps can be followed for rest of the 50 images or 100 images if you have, by recording this macro. Okay, so this is the purpose of macro recording. Okay, so that's about macro recording, and now we'll move on to the intensity measurement. And before that, let me just close all these things. Okay, now I'll show you how to do the intensity measurements using ImageJ or Fiji. So there are different terminologies that are being used for intensity measurement. The first is known as mean or average intensity. Okay, so let me just open an image first. So this is an image of DAPI stained nuclei, and you can see 5 DAPI stained nuclei, and they have different intensities, right? This nuclei is bright, and this nucleus is not that bright, like this. Okay. So let's say you want to quantify the intensity of this nuclei. Okay. So how you can do that? Now let's say if you have to compare the intensity, and if you make the ROIs or the region of interest like this, I won't make ROIs like this. I will go for a freehand ROIs, and I will make the ROIs like this. This is one, and I will also open ROI manager so that I can save all these ROIs. Okay, so ROI manager, run. So this is ROI manager, and I will save this ROI as first ROI. Then I will make another ROI here. I'm not making very precise ROI, but let's say if your application needs the precise quantification, you should make the precise ROI. And to make the precise ROI, what you can do is you can take this zoom tool and you can zoom your object like this, and then actually you can make the ROI in a more precise way like this. I'll add this as a ROI 3, then show all, and again I will zoom this nuclei. I will make the ROI like this, region of interest. Oh, I didn't add the previous ROI, so let me go back, add T, and this is my 5th ROI. Okay, and add T. So see, these are 5 nuclei, and we make the ROI against each of these, right? And our intention is to measure the intensity, fluorescence intensity, so that you can say that, let's say this ROI has more DNA compared to this ROI. Okay. So now intensity can be measured in several different ways. The first type of intensity is the mean or average intensity. So average intensity means it's the average intensity is the average pixel intensity over all the pixels in an object or ROI. So let's say this ROI has so many pixels. Okay, this entire image is 512 by 512 pixels. Okay, so this ROI has several pixels. So it will measure the intensity of individual pixel. If you enlarge it, you can see each pixel, right? So it will measure the fluorescence intensity of each of these pixel, and it will take the average of it. Okay, so that is the average ROI or mean ROI. The second type of ROI intensity is known as integrated ROI, or the integrated intensity or the integrated density. Okay, so integrated density is the sum of the pixel intensity over all the pixels in an object, or ROI. Okay, so in integrated intensity, what it will do or what it will measure, it will take the fluorescence intensity, it will measure the fluorescence intensity of each of these pixels and just sum it up for so many pixels. Okay, it will give you one number that okay, the total sum of this intensities of all the pixel is this amount. Okay, so that is known as integrated intensity. Integrated intensity. Now, in which case you should measure which type of intensity? Okay, so let's say here you can see your objects are of different size and shape. Okay, they are not of the same size. Okay, so in this case, if you have to measure you have to compare the fluorescence intensity, then you should go for mean intensity. Okay, because if you take the mean intensity, then you will get to know that whether the mean intensity of all this pixel is higher than the other nuclei or not. Okay. Even if you go for integrated intensity, then also this kind of nucleus will give you higher intensity because most of the pixels are brighter than the other nuclei. Okay, but here it will also sum up the intensity of some of the dark pixels, because see here, while making the region of interest, we selected some of the dark pixels. Okay, like this. So it will also add the intensity value, although it is more or less zero intensity because there is no signal here, but it will add those values to your calculation. Okay. And if you take the average intensity, then what will happen? Your average intensity will go down because you have included so many dark pixels while making the region of interest, right? So ideally, for this kind of experiment, you should compare the integrated intensity rather than average intensity, because see, here you have made the region of interest in such a way, so some of the dark pixels are also covered. Okay, and if you take the average of all these pixels, then these dark pixels will bring the average down for the rest of the bright pixels. Okay, whereas if you go for the integrated intensity, it will sum up the intensity of all the pixels, including the dark pixels, but as said, the dark pixels are not giving any fluorescence, so they will not change the overall number significantly. Okay, so for this kind of analysis, where the size and shape of the objects are different, you should always go for integrated intensity. And here you can see the relationship between the average intensity and integrated intensity. So if you know the number of pixels in this region of interest, then you can calculate the average intensity from the integrated intensity. So if you divide the integrated intensity by the object area in the pixel, then you can get the value of the average intensity. Then the other type of intensity is known as maximum intensity. So maximum intensity is let's say there are so many pixels in this nuclei, but what is the intensity of the brightest pixel? So that is the maximum intensity. So out of so many pixels, one pixel will be having the highest fluorescence intensity. Okay, so that is the maximum intensity. And the minimum intensity is the intensity of the dimmest pixel. So let's say there are so many dark pixels, right? So it's the fluorescence intensity of the dimmest pixel, so which is showing very weak fluorescence. And in which unit the fluorescence intensities are quantified? So fluorescence intensities are quantified in the gray levels. Okay, so the unit of this fluorescence intensity is the gray levels. So I will show you here one small exercise. Now you can measure this intensity in two ways. First one is plot profile. So let's say what I will do, I open this DAPI.tiff file and draw a line across the particle. So I will take this line tool and I will draw a line like this, passing from the nucleus. And then I will go to Analyze and Plot Profile. Analyze and Plot Profile. So see, this is the fluorescence intensity of this line, and you can see there is a weak intensity in the middle, so you can see the signal shows according to that intensity, and there are low intensity on both the sides, both the sides. So you can see those intensities are mostly close to 0, and you can see the unit of this intensity, that is a gray value. As I mentioned, that the unit of the fluorescence intensity is the gray level. Okay, so this is a unit of the fluorescence intensity. Okay, now if you want actually the numbers of this fluorescence intensity, because here you are seeing the graphical representation, but let's say you want to plot it in a different way, then you need the numbers. Then you can just click on this list. Okay, so it will open this kind of a file in which pixel to pixel gray value is mentioned. So first pixel, the gray value is 0. Second pixel position is 0 here, and the gray value is here. Okay, so you see initially some pixels are having 0 value. Then as you go along, the fluorescence intensity, the gray value will increase. Okay. Then again that center area, the intensity is low, so it will go down. See, this is the center area, so again the intensity has gone down, and then again it will increase, and then again it will be close to 0 in this area where there is no signal. Okay, so this you can save as plot values, and you can open it as a .csv or the Excel file. Okay, and then you can manually do whatever the modifications you want to do, or if you want to plot it in a different way, that you can do. Okay. Also, you can convert it into live mode. Okay, so here is a button, and you go to live mode, and now you can change the position of this line like this, and you can see the changes in the fluorescence intensity in real time. Okay, like this. You move the line, it will keep changing the profile accordingly. Okay, so this is the function of the live command. Okay, and I will close it now, and I will also delete this line also. Okay, now another way of intensity measurement, that was a line profile, but let's say you want to measure the intensity of this entire area. Okay, then what you will do? So you will draw region. So we already drew regions, and we save each of these regions as a ROI in the ROI manager. Okay, so these are our 5 ROIs, and I selected all of them. Now I will go to analyze and set measurements. Analyze and set measurements. Okay. And here I have to select that what I want to measure about all this region of interest. Okay, so I want area, then I want mean gray value, that is a mean intensity, plus standard deviation. Then I want to see the minimum and maximum gray value, like minimum and maximum intensity. Then I also want integrated density. Okay, so that is this one, integrated intensity. Okay, and if you want to center, you can click it, but at this point we do not need it. And yeah, and I will press OK. So it will measure this many parameters from this region of interest. And now I have to select this all 5 ROIs, and I have to press this button, measure. Okay, so it will measure those values for all these 5 ROIs. Sorry, not rename. I'll press measure. Okay, so here you can see the area for each of these ROI, mean intensity, standard deviation, minimum intensity for each of these ROI, maximum intensity, integrated density, raw integrated density, and some threshold value. Okay, so see, by visually you can see that area wise this is the biggest area compared to others. So you can see that 395 is the area. Okay, and here everything is in pixel. Okay, so 395 pixel square, that is the area. Okay, then mean intensity is, you can see this is the highest, as we can visually see, it's 160. No, this is not the highest one is the fifth one, 164, and I think that is this one. Okay, now that is the thing, though visually you can see this as a brightest nucleus, but why this is giving you the highest mean intensity? Because here we have covered so many black pixels. Okay, as you can see, while making the region of interest, we included so many black pixels. So if it will measure the fluorescence intensity of this black pixel, it will be 0, and it will take the average of those values along with the average of all these pixels. And that's why, though this is the brightest nucleus, in the intensity wise, if you see, it is not the brightest because of reasons of lot of black pixels. And that's why for this kind of estimation, you should not go for the mean intensity. Okay, but instead, if you go for this integrated density, which is irrespective of the black pixel. Okay, so you see this ROI is giving the highest integrated density, that is 63,859. So that is the sum of all sum of intensity values of all the pixels. Okay, and the lowest one is this 23,684. So I think that this is the third one. Okay, and I think you can give label also. So 1, 2, 3, 4, 5. Okay, so third one is the lowest bright. Okay, and the first one is the brightest nucleus. Okay, so this is how you can measure the fluorescence intensity, and when the area of your objects are not same, at that time you should go for the integrated density. You should not go for mean intensity. You should only go for mean intensity if the area of the object is the same and you are making ROI very precisely, like by after zooming the object, and it should not cover the black pixels like this. Okay. Okay, so I think that's it for intensity measurements. We already discussed about this, what to select in the SAT measurement menu. Yeah, that's it about intensity measurement. So I'll close this images. You can save this result file as a .csv file, and you can open it in Excel and you can do further calculations based on these intensities. Okay, now the third thing of today's class is the co-localization. Okay, so how to do the co-localization analysis using ImageJ, and what is a co-localization? So let's say you have labeled two different proteins with two different colors. Let's say this cytoplasmic lake 1 is labeled with green color and this dynein is labeled with red color, and you want to see whether these two proteins are co-localizing or not. So generally what people do, they just take the image in green and red and then they merge, and if you can see this yellow pixels, that means those two proteins are co-localized. Okay, but it will not tell you the extent of co-localization, because here along with yellow pixels I can also see some of the red pixels, some of the green pixels. Okay, so that means not all the pixels which are in red color, they are localized with green color. Okay, maybe some partial overlap is there, but not the complete overlap, and I do not have any quantitative number that represents the extent of co-localization or the degree of co-localization. Okay, so to measure the co-localization in more robust way and more mathematically, there are two coefficients that we are going to discuss today. So understanding the colocalization coefficients. So rather than relying on the inaccurate colocalization color, the purpose of the colocalization coefficients is to characterize the degree of overlap between two channels in microscopy image in a mathematical term. The two most commonly used indices are Pearson's coefficient and Mendler's coefficient. Okay, so I will show you what these coefficients are and how to measure them. Okay. So here is one caution. Our visual systems trick us. So you can see the same biological sample with three different color combinations. Okay, in one, this protein is shown in green. In second, this protein is shown in red. And in third, this protein is shown in blue. And similarly, the colors of other proteins have been changed. Now you see, what are the proteins? You may find that they are colocalizing here, but the same protein you will find that it is not colocalizing if the colors are changed. Okay, so our color perception is brightness dependent and the brightness perception is color dependent. And the color perception is also influenced by the surrounding colors. Okay, so just by looking at this image and by looking at the colocalization of these two colors, I cannot say that these two proteins are really colocalizing or not, or even their degree of colocalization, their extent of colocalization, that I cannot say, because that keeps changing with different colors and different intensities. Okay, so that's why we need those kind of Pearson's coefficient and Mendler's coefficients for the accurate quantification of the colocalization. So what is Pearson's correlation coefficient? Pearson's correlation examines not the colocalization of red and green pixels, but instead it examines the degree of synchrony of the two colors. That means it asks a simple question. If one looks at every pixel of the image, when the intensity of the green deviates from the mean, does the red intensity do the same? If the two colors are 100% synchronized, the value 1 is assigned. If the red and green are repulsive, the value of -1 is assigned. And if there is no correlation whatsoever between red and green, a value of 0 is assigned. So the Pearson's coefficient of value of 0 represents that there is no colocalization. The Pearson's coefficient value of 1 is represented as 100% colocalization. Okay. Now, what is Mendler's overlap coefficient? So Mendler's overlap coefficient provides a ratio of intersecting volume to total object volume. This interpretation holds true strictly only for the limiting case where the object's volume in each channel is roughly the same and when the intensities inside the objects are relatively constant. One advantage of Mendler's coefficient over Pearson's coefficient is that the Mendler's calculation is channel specific. The M1 and M2 coefficients are defined separately for each channel to quantify the portion of the intensity in each channel that coincides with some intensity in the other channel. So let me show you this thing in more practical way. Effects of increasing spatial overlap. Okay, so see, this is a 10 by 10 pixel image, and you can see there are 4 pixels in red, 4 pixels in green. Okay, and if there is not at all any overlap between these two red and green pixels, then the Pearson coefficient will be minus 0.108 and Mendler's coefficient will be 0.00. In channel 1 also it is 0, channel 2 it is 0 because there is no overlap. Okay. If there is a kind of 25% overlap between, so out of 4 pixels, there is only 1 pixel which is overlapping, then Pearson's coefficient will be 0.169, Mendler's coefficient will be 0.250, and in both the channel it will be 0.250 and 0.250 because red and green both are overlapping with the same extreme. If the situation is like this, okay, where half of the red pixels are overlapping with half of the green pixels, then the Pearson's coefficient will be 0.446 and Mendler's coefficient will be 0.5 because it is 50% colocalization. Okay. And let's say if it's a complete overlap, like let's say this entire green square, all 4 pixels of green, they are completely super overlap with red, then the Pearson's coefficient will be 1. Okay. And Mendler's coefficient will also be 1 in both the channels. So let us do one exercise here. Okay. And I will show how in the ImageJ you can use this colocalization plugin to quantify your Mendler's and Pearson's coefficients. Okay. So you will open an image actinium from the sample images folder. So this is your sample images folder and this is the image of actinium. I will open it. File, open, and this is the actinium image. Okay. So this is the actinium image that I opened and it has 2 colors, 2 channels, red and green. And I want to split those channels. So I'll use the command image color split channel. Image, color and split channels. So it will split this image into 3 channels, red, green and blue. So see, this is the blue channel. I will close it because there is no blue channel here. Okay, this is the green channel and this is the red channel. Okay. This is red and green. Okay. Now if I tell you that whether visually can you see that whether these proteins are localized or not, the red protein and the green protein, it's very difficult to say that, right? Because at pixel to pixel level we need to quantify the colocalization. Okay. So now how you can run the colocalization? Okay. So here we will run the colocalization. Go to Analyze, Colocalization and Coloc 2 plugin. Analyze, Colocalization, here it is, and Coloc 2 plugin. Okay. And here we have to define the channels. So channel 1 is red, channel 2 is green, then some other parameters mentioned here. Make these boxes are checked. Display images in result. Mendler's correlation, 2D intensity histogram and Costes significance test. Set Costes randomization to 100, that is already 100, and hit OK. Okay, so these are all default parameters and we are clicking OK. So now this software will analyze both these images pixel to pixel and it will give us the Mendler's coefficient and Pearson's coefficient in a few seconds. So we'll get something like this. So this is the 2D intensity scatter plot in which this side is the channel 1 intensity and this side represents the channel 2 intensity, and we'll get some result table in which you will see the Pearson's coefficient and Mendler's coefficient like this. Yes, so the results are here. You can see this 2D scattered plot with channel 2 on y-axis, channel 1 on x-axis. And here some more statistical parameters are mentioned. And here you can see your Pearson's coefficient is 0.74, which represents significant extent of colocalization because Pearson's coefficient towards 1 is better for colocalization. And Mendler's coefficient is 0.991 for channel 2 and 0.997 for channel 1. So both these values are very close to 1. So Mendler's coefficient also represents a very high degree of colocalization. Okay, so with this Pearson's and Mendler's coefficient, you can say that both these proteins are colocalizing to a huge extent, like almost like 99%, if you look at the Mendler's coefficient. Okay, and yeah, so this is how you should do the colocalization analysis. You can save this file and you can also save all these parameters. There is another log file also gets open along with this. So the same statistical parameters are mentioned in this log file. You can see the Pearson's coefficient, Mandler's coefficient, okay, and this you can save as Word or Excel file. Okay, I'll close that. So this is how you should perform the colocalization analysis, and just by saying based on the visual appearance that whether this red and green colors are mixing and they are giving the yellow pixels, and that's why these two proteins are colocalized. Instead of doing that, you can do this kind of mathematical analysis pixel by pixel to quantify the extent of colocalization. Okay, so that's it for today's class, and in the next lecture we'll discuss about single molecule imaging. Thank you for attending the class, and here we are finishing our ImageJ or Fiji based workshop, and next lecture will be a regular class. Thank you.